Hello, this is Dr. Hassan with Innovate, and this is lecture number 59, Derivation of State Graphs with the Application Design of Pattern Detectors, uh, of Chapter 9, Design of Synchronous Sequential Networks, of the course Digital Logic Design of Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design. However, there are numerous number of books in digital logic design. In Chapter 9, we are talking about practical applications to the design of synchronous sequential networks to show you how powerful this approach is, and it is a great alternative to microcomputers. Many complicated problems could be designed with finite state machine rather than going to microcomputer circuits, which are very costly, time-consuming, and complicated at the same time. Now, design problem number 1, we will look at a sequential network with one input X and one output Z. We would like to derive the merely static graph to recognize the pattern 1, 0, 1, 0, and patterns may overlap. As an example, for X, we have 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0. So the pattern occurred here, 1, 0, 1, 0, and output Z will be 1. Then the pattern occurred again, 1, 0, 1, 0, and the output would be 1. Then since they overlap, the pattern occurred at 1, 0, 1, 0, and the output will be 1. Then 0, 0. To allow overlap, we'll see the machine, how it looks like. So at S0, which is the reset state, if I receive multiple zeros, I don't need to remember it because the first bit of the pattern is 1. So I stay in S0. However, if I receive a 1, I need to remember it, I go to S1. If I receive a 0, I must remember it, I go to S2. If I receive a 1, I must remember it, I go to S3. If I receive a 0, I will go to S2 to allow overlap and the output will be 1. So if I receive 1, 0, 1, 0, 1, 0, 1, 0, see, it will give me 1, the Z will be 1 in every cycle. So you will get 1, 0, 1, 0, 1 for Z. And to do that, so from S3, I went to S2 to allow overlap. However, in S3, if I receive 1, 0, 1, 1, I need to remember only the last one, so I go to S1. In S1, if I receive multiple ones, I will stay in S1 because S1 will remember only the last one. If I receive 1, 0 followed by a 0, the pattern will be messed up, so I reset the state, reset the network by going to S0. So in S2, if I receive a 0, the output will be 0, and I go to S0. And this will be the conclusion to the solution number 1 of design problem number 1. In design problem number 2, I would like to design a nearly sequential network with one input X and one output Z. If the input sequence 0, 1, 1, 0 or 0, 1, 0, 1 occurs, an output of 2 consecutive ones will occur. The first of these ones will occur coincidence with the last input 0, 1, 1, 0 or 0, 1, 0, 1 sequence followed by the second one while the network is resetting. To do that, simply we go, actually, again, we have X, and once we detect 0 here, I have 0, 1, 0, 0, 1, 1, 0, 0. So I have 0, 1, 1, 0, I have 1 first at the last input 0. Then I have 1 at Z when Z will be 1 again. So we have 2 output of Z, which is 1, 1. So Z will be again an output, which is a following. So 2 consecutive output. And the second Z, the network will reset. Again, we have here 0, 1, 0, 1. So I get 0, 1, 0, 1. So this is the second sequence. So I get an output 1, and the second one with the network reset. So therefore, I am in S0. If I receive a 1, the first one is useless because I don't need to remember it, so I will stay in the reset state as 0 and the output will be 0. However, if I receive a 0, I will remember it, so I go to S1. If I receive a 1, I will remember it, I go to S2. If I receive another 1, I will remember it to go to S4. If I receive a 0, I will go to S5, and the output will be 1. From S5, if I receive a 0 or 1, I will go to S0 to reset the network, and the output will be 1. The same thing actually, if I receive the sequence or the pattern 0, 1, 0, 1, the output will be 1, and I go to S5. Okay, so here 0, 1, then I receive the 0, so I go and open a new state, which is S3, to remember the 0. So if I receive another 1, the output will be 1, I will go to S5. If the input 0 or 1, the output will be 1, and I will reset the machine. However, if I am in S3 and I receive a 0, the pattern will be 0, 1, 0, 0. This will be not our pattern, but we need to remember the last 0, so I go to S1. Again, if I am in S1, I receive multiple zeros or a single 0, I will stay in S1, and the output will be 0 because S1 will remember only a 0. And this will be the conclusion for solution number 2, the design problem number 2. In design problem number 3, a more sequential network has one input X and one output Z. The output Z is 1 and remains 1 when at least 2 input zeros and at least 2 input 1s have occurred. When we say at least, it may have multiple zeros occurred and multiple 1s occurred. But once you have at least 2 and at least 2 zeros and 2 1s occurred, Z will be 1 and will remain 1 regardless. So this is a beautiful problem and could be designed with 9 states. S0, the output 0. If I receive 0, 0, 1, 1, the output will be, I am in S4 and the output will be 1 and will remain. If I receive 0, 1, 0, 1. If I receive 1, 1 and multiple 1s here, then 2 zeros, I will go to S4. So any way that you look at the network will verify the condition. So we received at least, the network will remember at least 2 zeros and 2 1s as inputs or vice versa, and the output will be 1 and remains 1. This will be the conclusion for solution number 3 for the design problem number 3. In design problem number 4, a more sequential network has one input X and one output Z. The output becomes 1 when the input sequence 0, 1, 1 is recognized, and the output remains 1 until the input sequence 0, 1, 1 is recognized again, in which case the output returns to 0. It remains 0 until the input sequence 0, 1, 1 is recognized again, in which case the output returns to 1, and so on and so forth. So this is a beautiful machine, beautiful design where we are looking to detect 0, 1, 1. The output will be 0, the output will be 1 once we detect it, but once we detect it again, okay, the output will remain 1 until we detect it again, and so on and so forth. So the output will become 0, and so on, and we continue detecting 0, 1, 1, and the output will alternate between 0 and 1. So derive the network accordingly. So we will design S0 as the reset state. S1 remembers the sequence ends in 0 with 0 output. S2 remembers the sequence ends in 0, 1 with a 0 output, and S3 will remember the sequence 0, 1, 1 with the output is 1, followed by S4, which remembers the sequence, okay, again, which is followed by S4, S5, and S3, S4, and S5. So we have the sequence here. Initially 0, 1, 1, and the output will be 1. S3 will be 1. Then we detected the sequence 0. So we detected the sequence 0, 1, 1. We detected the sequence 0, 1, 1. The output will be 1. If we detected the sequence, if I am in 0, So S2 will remember the sequence in 0, 1. And S3 will remember the sequence 0, 1, 1, and the output will be 1. So S4 will remember what the sequence here in S4. So if I receive actually 0 in S4, the sequence, the S4, the output will be continue to be 1. But once I receive a 0, 1, 1 again, the output will fluctuate back to 0. So S0, the output will be 0. So I receive 0, 1, 1, the output will be 1. I receive 0, 1, 1 again, the output will fluctuate to 0. So if I receive 0, 1, 1 again, the output will become 1. It will stay 1. So once I receive the sequence 0, 1, 1 again, it will become 0, the output will become 0, and will stay 0 until a 0, 1, 1 again will occur. Now, if while we are detecting 0, 1, 1, if 0 repeated itself many times, like 0, 0, 0, 0, 0, 1, 1. So if I repeat 0, S1 will retain 0, so I will remain in S1. Now, if I am in S2 and I get 0, 1, 0, I need to remember only a single 0, which I go back to S0. If I remember 0, 1, 1, then I got multiple ones. So the multiple ones will force me to stay in S3. Okay, so to remember, because S3 will remember only 0, 1, 1. So multiple ones, I will stay in S3. Now, if I detected 0, I will go to S4. If I get multiple zeros, I will remain in S4, and the output will continue to be 1. However, if I get actually 0, 1, 1 again, the output will switch back to 0. If I get multiple ones in S0, I will remain in S0. Because I will get here 0, 1, 1, then 1, 1, 1, I will remain, and the output will be accordingly 0 until the detection of the complete code, which is 0, 1, 1, will take place and fluctuate back to 1. So the network will be a perfect solution. And to design a problem number 4. We'll go to the next one, which is design a problem number 5. A merely sequential network has one input X and one output Z. The output Z is the input X delayed by 2 clock cycles. Now, this is very useful in control systems, in digital control systems. You delay the output by a number of clock cycles. To do that, I have the input 0, 1, 1, 1, 1, 0, 0, 1, 1, the output delayed by 2 clock cycles. So I will get 0, 0, 1, 1, 1, 1. Okay, and the network will look like this. It is a Mealy network. I have the reset state as 0. If I receive a 0, I will remain in as 0. If I receive 1, 1, the output will be 0, 0. Then I receive 0, I will go to S2, the output will be 1. If I receive another 0, the output will be 1. The output will be 1. So this will be a delay by 2 clock cycles. So 1, 1, 0, 0 will give me a 0, 0, 1, 1. If we look at the pattern, for instance, 1, 1, then if I have another 1, I receive a 1. So I have to stay in S3 because S3 will remember really 1, 1. So the output will be 1 because after 2 ones, the output will be 1. If I receive actually in S2, if I get 1, 1, then 0, 1, 1, then 0. So the output will be 1 here because this will be delayed by 2 cycles. And if I receive another one, the output again will be 1 because I have 2 ones will be received. If I am in S0 and I receive 1, the output will be 0. Then if I receive another 0, the output will be 0. Now, so we'll get 1, 0. If I receive a 0, the output will be 1. The output will be 1. And if I receive 1, the output will be also a 0. So however you look at it, you'll see the output Z will be delayed by 2 clock cycles from the input X, and by doing that, you will have the complete design for the design problem number 5. Now, very interesting design is the next problem. This is how encryption and decryption is done with finite state machine. We have a machine which is at the transmitter side, encrypt the data. So encrypt the data and set an encryption scheme. So a sequential machine, N1, which is shown here, is a part of a transmitter and is used as a serial data converter to convert a data stream of original to an encrypted message before transmission. The receiver receives the coded message and convert it back to, so we need really to design N2 of the merely state graph of the transmitter network N1 is shown. Derive the merely state graph of the receiver network N2. So how this data is, I have, if I receive multiple ones, if I am in S0, so if I receive, for instance, 1, 0, 0, if I receive 0, let's say it receive only 0, 0, 0, 0 will convert to 0, 1. If I receive a 0, 1, it will become 0, 0. Then if I receive another 0, the output will be 1. So this is an encrypted data. So to get the decryption network, what I will do, I will flip. I will exchange X with Z. Okay? So we'll do the inverse. So for every X, Z, and for every Z is X. So we'll swap. 0 will remain 0. So those will remain. 1, 0 will become 0, 1. 0, 1 become 1, 0. And 1, 1 will remain 1, 1. So the solution for the decryptor is network 2 as shown. So I will have complete design and a complete solution by swapping X and Z for every other in the network N2. We will decrypt the data and you can try it. Okay? And by doing this, we design an encryptor and decryptor machines, which is a beautiful application in data compression and encryption. By this, actually, we finished another set of applications for the finite state machines. I thank you so much for listening. Please subscribe by clicking on the blue circle and give me a thumb up. And hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.